Clara. Chiara will begin her second talk. So thank you, Chiara.
Okay, very good. Thanks for making my name Spanish, Clara. Okay, very good. So we are here back for the second class. And so I wanted to maybe clarify, I think it's useful to clarify some points that arose in the past lecture, because I realized that maybe I glanced through a bit fast for through definitions. So for instance, definition of surface gravity and the relation to the temperature. I give you here a heuristic explanation why you can get it from the derivative of the work factor. So I'm just going to sketch here a few points from the first class. So the first point here, so it concerns the surface gravity and the Euclidean metric. And as I said, this came from one of your questions. So if you have, for instance, a metric that looks like this, with a warp factor V of R, this is like a Lorentzian metric. And for instance, the AdS Reisser-Nordström fits into this class of metrics. For instance, V of R for the Reisser-Nordström is something like V of R equals 1 minus 2m over R plus Q squared over R squared. Example, so for this one, so if you define a quantity, define a quantity which is kappa, that would be the surface gravity. If you define it in this way, 1/2, you take the derivative of V prime, so derivative, so V prime of R, compute it at R equals R plus, where R plus is a root. So R plus is a root of V of R. So in this case, will be the outermost root, will be the outermost horizon. So if you can take this metric here, you change the coordinate. So introduce a new coordinate. So this is just like you evaluate the derivative at R equals R plus. You mentioned that in the case this is a number. So introduce the coordinate rho, which is square root of 2 k to the minus 1 R minus R plus, that parameterize the distance from the horizon. So the metric close to R equals 0 to rho equals 0 reads like this. ds squared equals the rho squared plus, I'm going to write it in this term, so R squared. I'm going to single out like I kappa squared dt squared plus R plus squared the omega 2 squared. So okay, I put it here just a bit below. So this is the metric that you get once you redefine the coordinates in this way. So this is just the Rindler space, like Minkowski, two-dimensional Minkowski written in Rindler space, as I was mentioned before. But you can also see it now that if you weak rotate time, meaning that if you incorporate I, like this I into T, so basically you define T equals I T Euclidean, as Alejandra did it in her lectures. So you just neglect this one, and then you put TE. So this metric here is just a metric of Euclidean two-dimensional space. So it's just flat two-dimensional space, which is perfectly regular at R equals 0, provided that you can take TE to be like an angular coordinate. So this is d rho squared plus rho squared is just two-dimensional space, two-dimensional flat space written in polar coordinates. The metric at rho equals 0 is indeed regular if TE has periodicity 2 pi over k, right? So basically, metric metric is regular at rho equals 0, so at the origin, if TE is periodic of 2 pi over K. And Hawking temperature, TH, is nothing else other than the inverse of this period, so kappa over 2 pi. Because in general, you know that the periodicity of the Euclidean time is really related to the temperature of your system. Like, this is a relation that you find, for instance, in when you study, for instance, condensed matter, or when you study the Euclidean path integral. So in general, you have that from here. So this quantity here arises because when you really, like, let's say, when you expand the metric at first order, you get that the coefficient here is the derivative, is the first thing in the expansion that really trickles down into this term here. So that's why whenever you want to find the temperature of, for instance, a black hole which is of this form, whose metric is of this form here, which is a pretty common metric, what you do to find TH is that you first compute the surface gravity, which is given by the derivative of the GTT term. So this is something that I've used yesterday, but I didn't quite justify. So some of you asked, and I think it was good to just rectify. Then also, so let me just take a bit of other observation just to recap from the previous lecture. So we have seen that there was a small, large phase transition, large black hole phase transition, so at fixed charge, when the charge was lower, lower with respect to a certain threshold, like for Q, smaller than a critical value. That depends indeed on the value of the cosmological constant, for instance. And some of you asked, the phase transition looked like this. So plotting the potential, let's say the free energy versus the temperature, look like this graph here. The name of this graph, by the way, is the shape of this graph is the swallowtail. So swallowtail is like swallow is like a bird which has the tail which is really like in the form of the V. So this is kind of the shape here. We know that at this point here you have a phase transition between small black holes and then large black holes. Some of you asked what happens in the grand canonical ensemble. This is something that we can do it as an exercise, like in the latest, like in the next hour. But just as a preview, what happened in the grand canonical ensemble is that another configuration starts kicking in. So you will have small and large black holes, but also AdS, thermal AdS, the chemical potential will start contributing to the ensemble. And for a small enough chemical potential, you will have a graph like this, free energy versus the temperature. You have two states, large black holes, small black hole. AdS, thermal AdS space will have a line of constant free energy, which is set to 0, like as a reference frame. So the phase transition will be between thermal AdS and the large black holes. But I'm going to discuss a similar phase transition now, which is called the Hawking page phase transition, which is something that I'm familiar, like I believe that most of you at least have seen at least once. It will be very, very similar to this kind of here, to this configuration. And the last thing that I want to say as a recap, just to elaborate on what we found yesterday, is that indeed, so in general, we have seen that along a phase transition, you have in general some reorganization of the geometry of the black hole. In that case, we have seen that from a small black hole becomes large. But if the geometry is also supported by some matter, for instance, you can have black hole configurations which are supported indeed by gauge field, but also scalar fields. And the scalar fields are also subject to some change, for instance, along the phase transition. And what we have found, for instance, for similar charged black holes of the scalars, is that the scalars along the phase transition, let me just put it here. So along the phase transition, along the small, large phase transition, scalars are also subject to change. So indeed, if you plot, so the scalar, so in general, when you have a scalar configuration, well, when you have a configuration supported by scalars, the asymptotic value in the expansion of the scalars give you an information about the VEV and the source for the dual operator, the operators in the conformal field theory. So in general, you have an expansion of this term. We are in 4 dimensions, and for these kind of black holes that we have found that indeed they are supported also by scalars, imagine schematically you have a scalar, and around the boundary, it goes like this. These are the asymptotic expansion plus dot, dot, dot. So in general, depending on your boundary condition, but for us, this will be the source, and this will be the expectation value of the operator in the dual field theory. So these are beta. And if you plot beta, you have 2 different behaviors based on the fact, again, that Q is smaller than Q critical and Q is bigger. So for Q bigger than Q critical, once again, the value of beta respect to temperature is a monotonic function. But again, as you see, like as you might imagine, along the phase transition, something funny happened, and you have a behavior like this. So basically, the phase transition, again, is along this line here. So as we have seen also from the plot of the temperature versus the entropy, you also have this sort of reentrant phase transition here. We didn't manage to really show in our paper the fact that the area is the same here and here. This is still up to debate. But in general, also in the expectation value of the operator, you have a jump. So the matter supporting the configuration along the phase transition is also subject to some change. And this is even more useful, for instance, when you're trying to model some phase transition in the dual field theory by means of black holes. So for instance, another phase transition that we'll discuss in this lecture will be the holographic superconductor phase transition. And in general, for that case, the presence of further matter allows you to model the presence of a Cooper pair condensate. So, okay, I gave a bit of a recap of what we have found now. So this lecture, in the first part of this lecture, I will tell you a bit more about the possible phase transition that can arise for black holes. So in general, in the first class, we have seen that indeed even a very, very simple configuration, such as the AdS Reisner-Nostrom, has a very rich thermodynamics. And we have traced back this to the fact that AdS space acts like a box, and thereby, like, it is possible for a black hole, like at finite temperature, to be in equilibrium in AdS space. And many different black hole branches arise, and phase transition between them can happen, indeed. So this is a general rule. So I'm going to explain now other kind of phase transitions. And we first start with the phase transition, which is really similar to this one that I have drawn there. And the first phase transition that we are going to discuss today is the Hawking-Page phase transition. This is really something that is textbook, and you might have seen it before. Hawking-Page phase transition, and it dates back to, I think, something around the 80s. So for this sort of like phase transition, we are going to compare 2 different uncharged.
Excuse me, what is the expectation value of this? Or, I don't know.
Which one? Sorry.
Above the second graph.
Yes. So this is like an expectation value of an operator in the dual field theory.
Okay.
So in general, so for these black holes, whenever you have an asymptotically AdS black hole, you can map this into a system in the dual field theory. You can map it into a conformal field theory. And in general, all the asymptotic values for the scalars, they give information about the expectation values of operators in the dual field theory. So that's why the presence of matter in general gives you some order parameters to characterize the phase transition in the dual field theory. So indeed, another thing that indeed is also like, it should also be clear is that we are also, in addition to the fact that indeed for AdS black holes you have this rich thermodynamics, you also have dual field theory pictures. So you can model by means of black holes. So the phase transition for black holes, most of the times, they're kind of easy. You see, like you can plot this thing with 2 lines in Mathematica. But actually, the fact that with this sort of phase transition, you can model something which is strongly coupled in the dual field theory, because the holographic duality is a weak, strong coupling duality. So you can work with classical gravity in the bulk, and this is mapped into something which is strongly coupled in the dual field theory. And this is very like the power of the holographic correspondence, let's say. So for all these things, we have seen phase transitions between configurations which have charge. So allegedly, this is a simpler phase transition, which indeed involves 2 different kinds of configurations. So the first configuration is the simple like AdS space. Yes?
I mean, how do you know that you're finding the Hawking temperature if you have more than one horizon? I mean, kappa, it seems to depend on which R plus you are evaluating, right?
Yeah, exactly. It depends on the horizon at which you evaluate it. So you have different kappa. In general, for what you have, like since you in general work with the space-time, with the universe, which is really just outside the black hole, you use use just the outermost horizon, basically.
Oh. You are stick to the outer horizon?
You stick to the region outside the horizon. This will also have some, let's say, some intuition or some, let's say, justification for the fact that indeed, like you would like to have a geometry which cups off smoothly, like an Euclidean geometry that cups off smoothly at the outer horizon, so in such a way that it's very regular. So your space-time eventually ends at R equals R plus.
Okay.
But indeed, it's true. So you will have many different horizons, and in principle, you can compute kappa at whatever kind of horizon. If you have, for instance, a black hole in de Sitter, you have surface gravity, which is relative to the cosmological horizon. So a black hole in de Sitter, okay, I'm just going a bit as an aside now. So you have a black hole in de Sitter. Schematically, you have a black hole, and it's surrounded by a cosmological horizon. So you will have a temperature, the cosmological horizon also has temperature, because you can compute this thing here. Yeah. But you will also have a temperature of the outer horizon of the black hole. And in general, these are not equal. That's why, for instance, in de Sitter, having a black hole in equilibrium is a very, very special requirement. It's a very special point, which is called the lukewarm configuration. If there is time, I will deal with this on Friday.
Okay, that's good.
But yes, it's a very good point. But yes, for our purposes, or at least for you are required to have a regular solution that cups off smoothly at the outer horizon. So you always consider R plus. So okay, so let me go now through the Hawking page. So first of all, the Hawking page is a phase transition between AdS space filled with gravitons with a temperature and a Schwarzschild AdS black hole. So that's all solutions which are not charged. So we take AdS space written in global coordinates. And this will take it to be like this is the Lorentzian signature. This is AdS space. And then the second configuration that we are going to compare it with would be the Schwarzschild AdS black hole. It is, yes, thank you. The Schwarzschild AdS black hole is this one. E omega 2 square. And so this geometry here, as you has a horizon, you have to find the roots of this polynomial here. You have to take the work factor, set it equal to 0. You find the roots. In particular, you find it R plus, the outer root. And then you can compute the surface gravity, from which you can get the temperature. So the temperature of the black hole which is also equal to 1 over beta as a definition. So it will be 3r plus squared plus L squared over 4 pi L squared r plus. So this is the temperature of the black hole. Also for these configurations here, as I was mentioning yesterday, if you remember a bit, you have 2 different branches of black hole. This is something that I mentioned en passant, let's say. But so you remember that we had 3 different kind of configuration for charged black holes. The fact that you don't have charge here makes this last branch disappear. So for black holes in AdS uncharged, if you plot this temperature here versus, for instance, R plus or versus the entropy, you have small black hole and large black hole branch. Again, the small black holes, do you remember, this is like negative slope. So someone remember what's the pathology here? If you have a negative slope? Exactly, negative heat capacity or negative specific heat. So this one, we don't expect this to be like to play a role in our ensemble. We expect these to be the ones that will play a role. But okay, so at this point, so we want to compare these 2 particular kind of configuration. I'm gonna write it here. And if you remember yesterday what we have, here. What we have done is, for instance, first of all, we have fixed the boundary conditions because we want to compare 2 solutions with the same particular in the same boundary. And then we compare the 2 thermodynamic potentials, right? So in drawing this graph here, we have computed the free energy, the Helmholtz free energy of these configurations versus the temperature. And we have set ourselves in an ensemble of fixed charge. This means that the 2 solutions have equal boundary conditions at infinity. So the same thing we are going to do for our 2 configurations. And the thermodynamic potential that we are going to use, that we implicitly did also yesterday, but I didn't mention to you because I just dropped in the thermodynamic potential as the Helmholtz free energy, which is the one like appropriate in the canonical ensemble. So we're going to compare the on-shell action of these 2 solutions, because this is really the thermodynamic potential that tells you really which one solution are dominating, which are the 2 solutions. And also for the 2 solutions, need to have so the boundary of these 2 solutions. If you take into Euclidean, so if you take T to I, T, A, so on and so forth, the boundary is still S1 times S2. So both solutions have boundary. Let's say Euclidean boundary is S1 times S2. In order to compare 2 different solutions, it needs to have the same boundary conditions, so the same boundary at R goes to infinity. So in general, what we need to do now is to compute the potential, thermodynamic potential for this solution that for us will be the on-shell action. So first of all, these 2 solutions are both solutions to the equation of motion, to the Einstein's equation of the same action, which is just Einstein gravity in the presence of a cosmological constant, which reads like so. Where, again, like lambda is equal to 3 over L squared. You have a negative cosmological constant, so you can have an AdS space as a solution. So the equations of motion, so if you compute the Einstein's equation from this action here, give this. This is just by taking Einstein's equation and then contracting it with the metric. Means that R needs to be, like the Ricci scalar needs to be constant, 6 over L squared. So computing the thermodynamic potential means that we take this action here and we plug in these 2 solutions here. So these are solutions to the equations of motion, mean that we are also allowed to use the equations of motion themselves. So on-shell action, so on-shell, I'm gonna distinguish between the action that you have and the on-shell action where we actually have imposed already inside the equations of motion. The on-shell action for both the two solutions, we can impose this constraint here, hence we get this. Square root of g d4x. So this means that for once we impose the equations of motion, the on-shell action is just equal or at least proportional to the volume of the space-time for these solutions here. This is square root of the metric. So you have to compute the square root of the metric here for this solution, and this will be the thermodynamic potential associated to it. We have a problem though, because in general, once you have asymptotically anti-de Sitter space, this action here diverges. So Alejandra yesterday gave you a prescription, gave you some counter terms. So she talked about AdS3. And indeed, if you remember, she mentioned the fact that, first of all, you need the Gibbons-Hawking term, the term with the extrinsic curvature. This imposes the Dirichlet boundary condition, but also takes away some of the divergent terms. And also you have other terms, which are in general function like of the boundary quantities. So in general, they are functions which are different variants of the boundary that added to this action here takes away the divergences. So this is the correct way to do this. So you perform this thing, which is called holographic normalization. You take this action here, you take away the counter terms. It results in two finite values for this one, and then you compare it. Let's say a shortcut to do this, that is also something that is, for instance, followed by the paper by Witten, where he discussed the holographic meaning of this phase transition, is realizing that indeed, so the two solutions has the same boundary. In general, they have the same counter terms. So it means that they are renormalized by the same counter terms. So it means if we take the difference between this and this, provided that the solution have the same boundaries, then I should be able to find a finite value for the difference between these two potentials. Is that all clear? I see some puzzling, some puzzle face.
I have a question. So in this particular case, perhaps in other cases it's more complicated, but you would say that I could not have gotten a straightforward result by subtracting both on-shell action solutions.
Yes,
okay.
I could have. So what I'm following here is a bit of a shortcut. So what you have to do in order to get the potential, thermodynamic potential for the solution is that you take the on-shell action, okay, and then you add counter terms. The counter terms will be, for instance, the Gibbons-Hawking term. Gibbons-Hawking term, that is something that, for instance, the Gibbons-Hawking that Alejandra wrote down is something like, okay, I think it's, okay, now I'm not sure the coefficient, but it's basically square root of h, where h is the boundary metric, the extrinsic curvature. You also have another term, like let's do it like here. For instance, the counter terms that Alejandra used, again, is 1 over 8 pi g, square root of h, Ricci scalar of the boundary metric.
No, yes.
So these two things, you add it to the action for both of the solution, you get a finite action, and then you compare the two potentials, and you see whether a phase transition arises. That's perfectly fine.
Yes.
But I'm using a shortcut because I'm imposing the fact that both these and these, given the fact that the Euclidean boundary is the same for the two solutions, they have the same counter terms. So they are renormalized by the same things. So if I take the difference between these two, AdS and the Schwarzschild black hole, the divergences automatically, they are deleted.
So if the Euclidean boundary is the same, it is automatic that the counter terms are the same, or
in general,
not?
yes.
Okay.
The counter terms are evaluated on the boundary metric.
Very good. Thank you very
So
much.
in general, yes. You impose that they are in the same ensemble, hence they have the same asymptotic follow-off.
Once you find counter terms, once you add the contour terms and have the potentials, how is it that the transition is shown here?
So I'm gonna show it to you now.
Okay.
But basically, so let's put it. I didn't show you last time, but basically, if I take the AdS Reiser-Nordström solution, which is the one that I showed yesterday, I compute this action here and I normalize it, I get exactly the potential F, which is M minus Ts, that I used yesterday. Yesterday, I just gave it to you for granted, just because it's the Helmholtz free energy that you use also in thermodynamics. But you do the same thing. So the potential that you get from the on-shell action is the same one as you would get from here. So OK, I'm using this shortcut just to avoid computing all these nasty things. It's actually not that difficult, but if we can avoid it, that's also fine. So what I'm going to do is that I'm going to compute. So this is just a volume, right? So the on-shell action is proportional to the volume, like square root of g, integrated over d4x for either this or this. Okay. So there are, as I will show you, there are some subtleties that you have to impose on the boundary that is the same, and this will give some constraints to you. In this case, there is no subtleties because the solutions are sufficiently simple. So, yeah, we need to think about it. But I guess if the boundary is the same, then you can always, and if you choose your ensemble appropriately, you can always subtract these two things, provided that you take really care into having the same ensemble and the same boundary conditions. But I'm going to think about it a bit more. I naively, for sure in this case, it's fine.
The coordinates were very different looking, it would be a nightmare to do that, right?
Exactly.
Such that the solution, even though they have the same boundary, it's not so obvious to identify the coordinates to make sure that...
Yes, you will need to, yes, you will, of course, it works here because the coordinates are the same, so you can actually have the same, like the integral that you perform here is the same. Of course, what he's saying is that, yeah, if the coordinates are very different, yeah, you will need to choose the same coordinate system such that you can subtract them, and then it's very hard.
I think another way of saying this is that both solutions live in the same place, right?
Yes, exactly. The same boundary, for instance, and so on. But OK, so this is, I just meant for this to be as a shortcut to avoid working through all of this. But it's a good point. So OK, let me go there to the computation of the potentials. So AdS, this metric here, we all know it. So we have to take the Euclidean metric, because this is like, in order to compute the potential, you need the Euclidean on-shell action. Same thing for the black hole. And so we are going to compute the volume for this, both for AdS space and for the black hole. So volume, so this is, I just call it like, instead of, OK, I mean, just call it I, but it's just the volume. So this will depend, so as I was mentioning, this quantity here will diverge, because the radial, I have to take the, like the integral from, over the radial coordinate, and if you have AdS, you are subject to divergences. So I'm going to use a cutoff. So instead of integrating all the way to r goes to infinity, I'm going to take a cutoff like big R to be large. Then we will see that when we subtract the two quantities, taking r to infinity, the difference will be finite. But so all I'm saying is that computing this for Euclidean AdS is amount to having the integral between 0 and beta over d tau. The integration, like the integration for AdS space goes from the origin of the coordinates, so for r goes to 0 to r goes to big R, which is the radial cutoff. The r squared, integral over, OK, sine theta d theta d phi. So this is the integral over S2. This is just this, okay? Just computing the volume, so square root of g d4x. Again, so this is AdS. So for the black hole, for AdS black hole, once again, my integral will depend on the radial cutoff. And in general, so from 0 to, I'm going to tell this thing, I'm going to put beta 1 and beta 0 for something that I will tell you like just in a moment. And again, I'm integrating over the, let's put the same notation, Euclidean time, okay? Then here, I will integrate for my black hole, I will integrate from R plus, which is where my Euclidean geometry caps off, to R equals big R, which is the cutoff. So I was mentioning here, our Euclidean black hole will have specific boundary, S1 times S2, and then it will caps off as flat two-dimensional space at R equals R plus. That's why the extreme of integration for the black hole goes from R plus to R, big R. And then again, you have the integral over the sphere, like it was like the same, okay? Yes?
Basic questions. Why do you choose like the cutoff? Sorry. Why do you choose the cutoff of both potentials to be like the same, like R?
So I choose the same radial cutoff because basically what I would like is that the S2, the radius of the S2 would be the same. In your metric, you have in front of everything, you have R2, which is, well, this what will give this one. And so you want the S2 to be at the same radius. What you have preceded myself in the train of thought is that also, so we want the same radius for S2. We want also the same radius for S1. This is just a bit tricky, and that's why I put here beta 1 and beta 0. So since we are working with a finite cutoff, we want the geometry at the hypersurface R equals R big to be really the same. So we want the radius of S1 for AdS to be the same as the radius of S1 of the Schwarzschild black hole. This means that beta, so beta 1 that I put here, for the warp factor, square root of the warp factor of the Schwarzschild solution to be equal to the temperature of the black hole, which I erased. It was written here. Let's see. So we call it beta 0. I call it here 1 over beta. So let's use the same notation. So beta square root of R squared over L squared plus 1 plus 2m, sorry, minus 2m over R. So this means that this is just the length of the time circle at R equals big R, this one. This is the periodicity of the time coordinate multiplied by the warp factor of the metric is equal to the one of the black hole. Is that clear, or is that, so if you remember the metric that we were working with, so ds squared equals, let's say, dt squared, R squared over L squared plus 1, plus other stuff. So this is the, like, you have to include the periodicity of this coordinate here, and you have to multiply by the square root of this. This is the length of the S1 circle of AdS, should be equal to the same thing for the black hole. This way, you ensure that you have the same boundary. And so now we are ready, because this means that we are set our two configurations in the same phase space, basically the same ensemble. And then we can then subtract the two, like, so the difference in these two Euclidean on-shell actions. We can do this. Delta I equals, okay, let's do this thing. Yes? Exactly, yes. Yes, yes, in general. Yes, you take the limit after you plug in this, in general. Yes. In general, you take it, yeah, you take after having imposed this, in general. So if you compute the holographic normalization with all these and these, you already put R goes to infinity here. You know that the action is without any divergence. But since you are subtracting two divergent pieces, then the limit you take it after. So you compute the limit here. So this is, so I'm not sure of the L factor, but it should be there, I think. Okay. And then you take the limit, R goes to infinity of I black hole minus I AdS. And this is proportional to like a positive coefficient. L squared R plus squared minus R plus to the fourth over 4GN. Okay, pi also, I'm not sure of the coefficient, but I mean, it's a positive coefficient that you can just neglect. R plus squared plus L squared. And so this shows that indeed, so the difference between these two actions here, let me just put it this way, is negative for large R plus, and it's positive for small R plus. So let me just write it here. So it's negative for large R plus, positive for small R plus. So you can compute actually here where like this is like R needs to be 1 over L. This is where you have a change in sign. So it means that at large R plus, the black hole is favored because this is more negative than this one. So at larger plus, you have that the black hole wins over AdS space. It also means like, I erased here the function, like the formula for the temperature, but it means basically that at large temperature, the black hole is favored, and at small temperature, instead, thermal AdS is the favored configuration. So let me just write it down here then. Yes? No, Oh, no, it's just I take a limit then, so you have to put everything together, and then the square root kind of goes away. But for this one, so you impose, so this is the integral that you're about to make, and this you impose it in your boundary, in your extreme of integration, basically.
At what point do I know that I have to make both of those square roots equal?
You use, so the integral goes from 0 to beta 1 in the first one in AdS. So the other integral goes from 0 to beta, and then you have a relation that expresses beta 1, because so you have an explicit temperature for the black hole, but for AdS space in general, you cannot give, like, for the metric itself, you cannot give any temperature, right? There's no intrinsic temperature. So you fix the temperature of AdS space to be such that the Euclidean boundary is the same, in particular, the size of ES1.
Okay, so you equal the two integrals, so you have beta 1 in terms of beta, but when you subtract
I subtract this one minus this one, and I take the limit R big. Eventually, the square root kind of like re-massages itself. But it's something that, yes, so this one comes from a boundary condition, and this thing allows you to express beta 1, which appears here at the integration, in terms of beta and these other things.
I wasn't sure if you had taken the limit, and that's what the square root
Yes, no, no, then, I mean, you take the limit, yes, R goes infinity, because eventually you want a finite quantity, and the subtraction of this thing with equal boundary is the thing that ensures you that you don't have divergences. Sorry? The temperature is slightly, so if you want to see the temperature, meaning as the inverse of the periodicity of the TE, is slightly different because you are evaluating, you want it at a hypersurface cutoff R, you want the size to be basically the same. And you measure the size of the circle is this one, because you compute it from the metric here, from the warp factor and from the periodicity of this. So you compute this thing, square root of this thing for AdS is this, square root of that thing for black hole is this one, okay?
Wait, but where does R plus appear exactly? Because
So R plus appears, for instance, appears inside beta. I erased the formula here. I erased the formula because initially I have written down T in function, T as 1 over beta. It's a function of R plus. I think you might have had it. I mean, I think I was around here. So yes, once you plug everything in, R plus becomes here. Here instead it's R, the cutoff. Okay. Okay, okay. So the upshot of all this is that we have seen that at some point this thing becomes negative, in particular for larger plus. So for smaller plus, instead AdS, like thermal AdS, is favored one. So it means that you have a phase transition between like thermal AdS and a large black hole. Remember that the large black hole have positive specific heat, so they are nice and well behaved, contrary to the small ones. So, but in general, the upshot of all this is that, so for large T temperature, so large R plus, but you can invert the relation. So at large T, black hole is favored. And for small t, AdS space filled with thermal radiation, so thermal AdS is the favored configuration. And in general, this was like the contribution from Witten, like in 98, I think, is to interpret the fact that the black hole, like a large T, the black hole is favored as the deconfined phase. So for instance, like this is elementary quarks that are, let's say, in the quark-gluon plasma. They are not into hadrons. And these correspond to the confined phase. Where indeed quarks are confined into hadrons. So in general, this is something that you see on, so in general, on the dual field theory. So this is the gravitational picture that you have, that the black hole is favored for large temperature and AdS is favored for small temperature. They correspond to this phase of matter, and this analysis here was done in the dual field theory, for instance, in the n=4 super Yang-Mills, where you really see that in general, the order parameter for the confined and deconfined phase is the Wilson loop. So the Wilson loop has a different kind of behavior. So in general, for this case, you have like an area law for the Wilson loop. And for this one, you have the perimeter law. For the Wilson loop. So in general, this is the upshot of the Hawking page phase transition. So we have seen that you have, in this case, two different configurations that are really competing in the ensemble, and AdS space is one of those. While if you fix the chemical potential, if you fix the charge of the black hole, as we mentioned, anti-Sitter space was forbidden because if you have just a single charge, it backreacts and it creates a naked singularity if you have no mass. So AdS space and a fixed charge is not in the same ensemble for the phase transition that we found yesterday. So okay, I'm just a bit behind schedule. So in the various examples of phase transition that I wanted to present you, these are the most prominent ones, which are the ones that really they date back to the 90s. But I'm going to give you, let's say, one or two more examples, just to give you an idea of what you can do really by playing around with the black holes and with putting some matter support in the configuration. Then you'll see that many different, like even more exotic phase transition arise. So I'm going to give you other two examples for them. So are there any questions, by the way, for this Hawking page?
I really, I'm trying to understand how can you have this picture of quarks and confinement?
Okay, this is, I just discussed the gravitational part. This is taken from the study made by Witten and so on that computed indeed the fact that for n equals 4 super young mills, like below a certain temperature, you have the area law for the Wilson loop. And then otherwise you have the perimeter law. And this gives you basically the force between the two quarks.
Yeah, but, okay, if I'm being too naive, you can, n equals 4 super young mills have confinement because it's a conformal field theory.
I mean, this is like something that is not quite a realistic thing, but yeah. Okay. That is true. I mean, this is just a computation, holographic computation made in n equals 4 super young mills, but it's not really like the QCD, like with gauge group SC3 that we like. This is just something that, let's say, it resembles, like this is just a qualitative picture of what a phase transition between a large black hole and AdS can give you, qualitatively, let's say.
Okay, thank you.
You had a question.
So you had shown a plot of the end of the temperature as function of R plus, and you identified that there was an R plus where the specific heat would change sign. Is it the same R plus that we get here? So what would be the correct function after I fix it with this?
No, okay, so, okay, I don't think I have an immediate answer to you, but what I can say is that if I understood correctly. So this is the picture between small and large black hole. There's a minimum here. I think the onset of the phase transition actually is here. Like there are certain kind of black holes which are still large with positive specific heat that, however, do not dominate the ensemble. But we can do the computation later. Just it's a matter of taking the derivative of the temperature to see where is this minimum compared to where is this one. I can find out for you. I don't know it on the top of my head, but.
And is it correct to say that this plot is strictly speaking not correct because it was based on the assumption that it was a black hole, but now that you showed that there are two geometries, we should redo this plot and draw a better plot? What would be the better plot?
The better plot would be to compute, for instance, given the potential that I wrote here, so if you want the potential, okay, now I just need to normalize things correctly, but it would be something like, this is temperature versus area. If I plot the free energy versus the free energy of the black hole, will be something like the one that I showed you before, something like this. Like these are the small black hole, these are the large black hole, and this is thermal AdS. So up to here, thermal AdS is favored, up to here, and then from here on, the large black holes are the ones which are favored. Okay.
I think you said, and I was distracted here. You can't generalize this to Reiner-Nostrom black holes, this phase transition. So that's my question, is you can generalize it with charge, with black hole with charge, if you have a, you can have like a thermalized AdS with a chemical potential at the border.
Yes, yes, you can do. So yesterday we did the Reiner-Nostrom at fixed charge, right? So if you do the same procedure that I did here, with the appropriate boundary counter terms that fix the charge and so on, you get the picture that I showed you yesterday. If you
Thermalized AdS with temperature and a potential, a chemical potential.
Yes, that would mean, yes, you will need to do the same with the, like, yesterday I showed you how to, how to figure out the phase transition with the Helmholtz free energy, which is the one that is appropriate for an ensemble of fixed charge. If you have to do the chemical to fix the chemical potential, you have to take the Legendre transform of this. So you will have the Gibbs free energy, which is the one that reads something like, okay, I'm being very sloppy here, but Gibbs, the function that you would need to extremize would be this one, minus phi q.
Okay.
And that you will have a similar picture to the one that I just erased here. But, and we can do it in the exercise. I mean, I think it's pretty straightforward. But yes, so given that you changed your ensemble, you also need to change, and this will be a boundary term that you have in your own shell action. Like, I can elaborate on it more, but this is the correct function to investigate for this for the fixed chemical potential. Okay, so and in general, the ensemble of fixed chemical potential is the one that is widely used in AdS-CFT in general. So, yeah. Okay. Any other questions on this? So if not, I'm going to give you maybe, because I'm running out of time, so I'm going to give you maybe other two examples of phase transition. Maybe one, let's see how long does it take. Yes, yes, I knew that. It's not like yesterday that I wanted. I have half an hour, yes, but I wanted to start talking about extremal and near extremal black holes, but I can still save some time for that. So other two examples of phase transition. So one of which is the very famous, so let me just sketch two of them. So the first one is the holographic superconductor. So another phase transition that you can have, indeed, is the one that involves, indeed, black holes with further matter. In particular, you can have a black hole system with a charge scalar. So let's say the action, yeah, okay, let's just do it. So the Lagrangian is really this one. I put like I name phi, like psi, as the scalar field. And the scalar field is charged under the gauge field. Let me mention that this one was discovered first by Gubser in 2008, and later elaborated by Hartnoll, Herzog, and Horowitz, pretty much the same year, like a very few months of distance. So in general, what you have here is that you can have two different competing configurations. So the first configuration that you can have is the AdS Reiner-Nostrom black hole. I'm not going to write again the matrix because it's something that we have like studied extensively yesterday. So this is one configuration that you can have, for instance, when the scalar field is set to 0. But another configuration you can have is the hairy black hole. Where you have that the scalar is non-trivial. So this is like a trivial profile. For the scalar. And this is non-trivial scalar psi. So what happens here is that, once again, like by tuning appropriately the mass of the scalar, you have that scalar goes as this at infinity. Plus dot, dot, dot. And as I defined before, depending on your boundary conditions that you put on the scalars, alpha and beta, in general, are the VEV and the source for the operators in the dual field theory. If you assume the Dirichlet boundary conditions, you set this one also to particular to 0, what is in general done. Beta is the VEV of the operator, the dual field theory. Sorry, beta is the operator AI. And you find that for a sufficiently small temperature, you have that for a sufficiently temperature, the hairy black hole is actually favored with respect to the bare Reister-Nostrum black hole. So I'm not gonna put here, not gonna do all the procedure, but you can find it in these two papers. In general, what they do is actually they fix the background, the black hole background, and they find some solutions for the scalar. But what it means is that for sufficiently small temperature, the hairy solution is favored, which means that there will be a non-trivial VEV, expectation value for the operator in the dual field theory. And this means that you will have a non-trivial OI. And this is interpreted, in this case, as the formation of a condensate of Cooper pair. And this was indeed this particular setup of black hole here. It's a planar black hole. Is said to be dual to a three-dimensional superconductor field theory, in which in the 3 dimension you have a superconducting system, because you have a non-trivial scalar condensate, which mimics indeed the fact that you have Cooper pair condensation, which is typical of what you have as superconductor. So okay, and once again, the last phase transition that I'm gonna give you here So I'm aware that I am just giving you this as an example. I'm not going to full details as I was for the Hawking page or for the Reister-Nostrum solution. The other, let's say, phase transition, but it's not quite a phase transition. It's like a system, holographic system, that exhibits some Glassy physics. So just to give you an idea of how many systems you can actually model via black holes, via holography. So the last one that I'm talking about is a Glassy system. And this was indeed like the conjecture that black holes could be due to Glassy systems was by, so Aninos, Anus, Denef and collaborators. So these people will be here next week. So feel free to ask them. They will always be very happy to talk about these conjectures of them. So this is another example of system that can be modeled via holography. This is particular glass. So glass is a metastable phase of matter. So in general, it's a non-equilibrium system, which exhibit many, like which exhibit basically a landscape of metastable minima. Also has some very high viscosity. because glass is a very, very viscous liquid, and it's formed upon supercooling, meaning you have a system, you cool it very, very fast. The system doesn't have time to reach actually the minimum or crystallize, and it exhibits the feature which is disordered as a liquid, but rigid as a solid. So this is a glassy phase of matter. So this gentleman here assumed the fact that, or at least put forward the fact that indeed a black hole horizon indeed behaves like a fluid. So there are the membrane paradigm for black holes that really like shows that indeed the equations at the horizon of the black hole at the horizon are really the one of a perfect fluid. So the horizon of a black hole is a perfect fluid, and once you supercool, can undergo a phase, some sort of phase transition into a system which is disordered and fragmented. So in this case, the somehow phase transition will look like a single center black hole turning into multi-center black holes. So a configuration in which you have, for instance, a big black hole surrounded by many different centers. So this in the picture is, let's say, transition that goes from one single center black hole to many black holes. So in general, this would be the liquid phase of matter, and this is the glassy phase of matter. This is motivated, indeed, by the fact that a configuration like this will be composed by many centers, will share, indeed, disorder. So the centers do not need to lie in a lattice, in general. But a system like this will be disordered as a liquid, let's say, but also rigid as a solid. Because, indeed, you have some electromagnetic repulsion between all the particles, is exactly balanced by the gravitational interaction. So a system of multi-center black hole shares the rigidity of a solid, but the disorder of a liquid. Notice that a process like this cannot happen classically. So classically, black holes have non-bifurcation theorems. So they satisfy non-bifurcation theorems, so you will need some quantum mechanical sort of effect to make the horizon split into many of them. Nevertheless, you can also just track the endpoint of this transition, and you see that actually this can still happen, like the two endpoints of the transition, you can analyze them separately at the level of thermodynamics, and this you are allowed to do. So what happens, what these people actually figure out, is that indeed, so you want to have this liquid phase at very big temperature, and the glassy phase when the temperature is lowered. And so their study was, indeed, put a black hole in anti-de Sitter, and study the stability of a small black hole, whose mass is negligible with respect to the previous one. And this, indeed, they found, by computing the potential of this probe black hole versus the radius, is that for temperature which are very big, the probe is always unstable. Means that the probe always wants to go into the horizon. This is the radius of the horizon of the black hole. However, when you start lowering the temperature, the probe starts being metastable. So at mid-range temperature, you start forming a minimum here. And if you lower the temperature very close to T equals 0, actually you end up having a stable minimum here. So this is at very, very low temperature. So this is the effective potential. Now I've sketched it very, 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 very fast. This is the effective potential that this probe black hole here feels on the background of a big black hole in AdS. Okay. So it shows here that indeed it seems that the picture that these guys really like put forward is really holding. Meaning for a very large temperature, the black hole, the single center black hole, which is corresponding to the liquid phase, is the favored like configuration. And when you lower the temperature, instead, this glassy phase of matter seems to be the one that it's like actually dominates the ensemble. And these people also corroborate this picture also, for instance, by computing the tunneling rate of these metastable solutions. So the tunneling rate between metastable probes inside black holes, they're related to some aging of glass, and so on and so forth. What is left to corroborate here, for instance, is there are some techniques that allow you to compute holographically the viscosity. So this system is composed by an AdS black hole and many probes. So this AdS black holes has a dual field theory, dual CFT3 or a dual three-dimensional field theory. And in order to compute the viscosity of this system, you have some techniques to do it on the gravity side. For instance, from the cross-section of low-energy gravitons. So what is left to corroborate, like what is left to, let's say, verify that this picture between a single center corresponding to the liquid configuration to the multi-center corresponding to the glassy phase, what is left to verify is that indeed the viscosity computed from this system here is very, very big. Because indeed the viscosity of a glass, like glass is a very, very viscous liquid. Like it's the most viscous liquid. And thereby, if you manage to compute holographically the viscosity eta, let's say eta over S of this system here, you really have corroborated the picture that this, let's say, holographic vitrification that takes you from this configuration to here is indeed corresponding to a glassy phase transition in a dual field theory. So, okay, so, yes? In general, well, okay, for these are systems, so let's say the answer is that both them and myself did this thing. So we embedded this system into string theory. So they are kind of very complicated systems in which these black holes are made out of the brains or membranes wrapping like some non-contractible cycle and so on. And so depending on the charge of this configuration, you manage to get three different kind of probes. And you can see that if you keep the same charges but you lower the temperature, you will find eventually that this is the favored solution. So I don't have now an answer for the parameter for this one, because actually in our paper we had, I mean, okay, I can look it up later in the paper, but then to see. But it's a very complicated system, so we didn't manage to get it analytical. So no, you don't have analytic solutions for the multi-center black holes in AdS. No, this is a long-standing problem. This is something that nobody managed to get. We also don't have any numerical solutions for that. We have solutions which are analytic but of naked singularity, in which both this one is a naked singularity, this one is just a probe. And what we have is just, probe computation, in which the mass of this is very, very big, and you consider this as a point particle on top of this black hole. That's why also the conjecture is still a bit far from being, let's say, verified. But this is just to give you one more example of how useful it is to find all these black hole phase transition. In general, with black holes, you can find like a lot, like just by checking their thermodynamic behavior, you find really, really a lot of phenomena that then you can interpret in the dual field theory and so on. But the upshot of this is that in general, the phase transition that you find in gravity is relatively simple. You find it just via GR, or eventually here, even with a probe computation. So you don't need so much, let's say, you don't need so much computational effort, let's say. But the picture that you get on the dual picture, like the things that you want to model in the dual field theory can be very, very complicated. It can be a strongly coupled system, can be something like, efforts in understanding glassy physics are still ongoing. People have some, for instance, infinite dimensional models describing glass, but I mean, it's still very much work in progress. Describing glass holographically would be really, really a huge advance. And in general, also for holographic superconductors or like cuprates and so on, the theory describing them is very strongly coupled. Describing them via black hole physics, like by means of holography, is very, very simple. So this is something that is for sure that has been driving a lot of the effort, for instance, at least for sure around the 2010s, like for the past 15 years, have been one of the driving, like one of the objectives of the people working in holography.
Sorry, I have one question.
Yes, yes.
You know how is the behavior of the entropy between the two regimes? Because look like counterintuitive. Counterintuitive. I don't know.
Yeah, in general, so the fact that the entropy or not, like it is, the fact that the entropy is, so how to say it? the fact that a configuration or not is favored is highly linked to the fact that you have like stable probes or not. So if you find stable probes, somehow you can derive it that the entropy of this system is bigger with respect to the entropy of the system with where the probe goes inside the black hole.
Yes, but the black hole solution with one center is a high temperature, right?
Yes.
Okay, so at high temperature you have less entropy.
Yes, yes. All I'm saying
Okay.
is that, so take at the same temperature a black hole without the probe and the black hole with the probe. In this configuration here, you will have that the configuration probe and the black hole will be of higher entropy.
Okay, it's like a example of entropic order. You know,
Maybe we
it's
will.
a recent.
Sorry?
It's a recent paper about entropic order.
Okay, maybe we can discuss it a bit later. I don't think I am a bit agnostic about that.
Okay, thanks.
But okay, so just to give you an idea, this is like something which is like recent. I mean, it's not quite recent, it's 10 years ago. Still a conjecture, but it's something that could in principle, I think it has much room for improvement and for development because it addresses something like the glass problem, which is something which is still like hard to tackle, let's say, with conventional methods. So using holography for glass is something that we could really think about, I believe. And I suggest that you try to also, if you want, ask the next speakers, like the speakers next week, what they think. But okay, so I still have 15 minutes. So since it ties a bit with this multi-center story here, and I will start introducing the topic of the next lecture, which is extremal and supersymmetric black holes. So for the moment, we have, if there are no other questions. So up to now, we have studied black holes in anti-de Sitter with temperature. We have, find a lot of solutions. We have studied the thermodynamics. We had scanned the entire phase space to see how they behave. When we fix the temperature, we fix the charge, we don't put charge, so on and so forth. We have seen that they can exhibit many phase transitions, and this is really nice. You can study them in the dual field theory, and so on and so forth. So this is like the first two lectures were about the really black holes, the very general black holes. So the ones that the topic of the next few lectures instead will be supersymmetry black holes, and in particular extremal black holes, which are very specific configurations. So we will see that imposing supersymmetry and extremality reduce your phase space really a lot. So why do we want to do that? Well, because in general, so via holography, for instance, we have a lot of techniques like they really arise due to the fact that you have supersymmetry. So supersymmetry is a powerful technique that indeed, in general, allow you to get results and to extrapolate results that you get easily at weak coupling to strong coupling. So in general, you have these techniques such as supersymmetry with which you can have results on, for instance, microstate counting. So we have seen that a black hole has a very big entropy. So it says like the entropy is much bigger than the star that formed the actual black hole. So having, take into account, or at least having some microscopic interpretation for this entropy is really something that we would like, right? Because the fact that a black hole has entropy, as I was mentioned in the previous lecture, really clashes with the fact that in general relativity, a black hole solution is just unique. So if you fix the mass, the charge, and the angular momentum, GR tells you just one solution. But the fact that black holes are thermodynamic ensemble tells you, okay, you have entropy, you have a huge entropy, you have 10 to the 96 states inside the black hole. So what are these states of? Like what's the interpretation of this black hole entropy? Well, it turns out that you can map these black holes, if you are in anti-de Sitter space, you can map them into a dual field theory via holography. So I'm sure that many of you know what holography is, like, raise your hand. Okay, I think that pretty much everybody knows. So via this, so the fact that you have supersymmetry allow you indeed to make computations in the dual field theory via techniques, for instance, of supersymmetric localization. And you can actually manage to count states in the dual field theory. So you map your black hole into the dual field theory, and you count states in this dual field theory, and these states should be the one that compose black hole entropy. And you can do this only if you have supersymmetry. So you have a very, very, let's say, rigid system. You have to impose a lot of constraints on your black hole solution. This is something that I will do in the next lecture. And so so the next lecture will be about very specific black hole systems. So in contrast with what we did here, which we worked in full generality. So we'll develop, I will tell you techniques, like, for instance, also the resolution of the killing spinor. We will work in theories of supergravity. Supergravity is a theory that indeed incorporates supersymmetry in general relativity. So we're going to work in theories of supergravity, and we're going to deal with the specific black hole solution which are amenable to microstate counting. So in the next 10 minutes, I will first introduce one specific requirements that these solutions need to have in order to be amenable to microstate counting. And the requirement is the solution to be extremal. So I think that I have talked a bit before about extremal solution once you asked a bit of questions, but let me, now I have 10 or 15 minutes, then I can just refresh your memory a bit with a very simple example, which is the example of the extremal Reisner-Nostrom solution. It's okay. You will see me writing all of this, like always a lot of metrics, but there is a very good reason for that. So this is the extremal, so this is just normal, like a generic Reisner-Nostrom solution in flat space, which is the easiest example that we have, okay? So dt squared plus dr squared over r plus q squared over r squared plus r squared the omega 2 squared. And once again, this configuration is supported by gauge fields, and the field strength is q over r squared. So we take the configuration to be purely electric. So I think that at this point, you're familiar with what we need to do to find the horizons. So the horizons are the root of this warp factor here. You have to impose this equal to 0. You get two values of the horizon, the inner and the outer event horizon, m squared minus q squared. And the temperature, I'm going to rewrite it a bit to be a bit more fancy. R plus minus R minus equals 4 pi R plus squared. So these are two horizons. So if you see here, in order for the horizons to be real, you have to impose an inequality, right? So the extremality bound is this one. Says that m should be greater or equal than absolute value of q. So it means, sorry, if you have that the mass is greater or equal than the absolute value, the thing under the square root is positive. So you have two non-coincident horizons. So one might wonder what happens if this bound is saturated. So if this bound is saturated, you have an extremal solution. So extremal solution is you have it where the mass is equal to the absolute value of q. So what you have, first of all, the two horizons coincide, right? So you don't have any more two horizons, but they're both at a radial coordinate, so this becomes 0. So this is both the two roots are at a coordinate m, which is also equal to absolute value of q. Also here you see that from the temperature, these are very special solutions, right? What happens to the temperature? Temperature is 0, yes. So the extremal solution has 0 temperature. Nevertheless, like if you compute the entropy, it is finite because you have to compute basically the the spatial two section here, evaluated at R equals M or equal Q squared. So the entropy of the black hole is finite, and also non-zero. So already we see it here that they are very special systems. It's a very special subset of configuration. Because in general, it's kind of tricky, right? You expect it that if a configuration has zero temperature, also why it why it does have this very big entropy seems a bit funny. So we'll see that unless you have supersymmetry, this thing will be actually modified. This will be the topic of the last class. But for the moment, keep it at face value, this thing. I was anticipating the topic of the last class. But what I mean is that, so as the solution it is now, you can see that it has zero temperature and finite entropy. This will be correct. Also, like correct in particular if you have supersymmetry. If you don't have supersymmetry, in the last class, we will see that there will be some problems with this statement. Because supersymmetry, so you don't expect to have, let's say, a very big number of ground states which are not protected by symmetry. That is the case here. You have no additional symmetry protecting, so you have a huge amount of ground states for zero temperature, and you might think that maybe quantum corrections might alter this, might lift these ground states. This is something that happens if you don't have supersymmetry, and this will be the object of the last class. So for the moment, take this as face value. The definition of the extremal solution is a solution that satisfies this, and somehow this comes out from just the classical general relativity formulas. So as a last thing for this class, I'm gonna just tell you what is the new horizon geometry for this solution. We have seen that once you have a non-extremal black hole or a black hole with temperature, such as the Schwarzschild solution, the new horizon geometry that I wrote in the very, very first blackboard there, the new horizon geometry is like just Minkowski two-dimensional Minkowski space written in Rindler coordinates, this one. But we'll see that in this case will be very, very different. So take M equals Q. Well, for the moment, we take Q to be positive just for simplicity. So the metric becomes this. It develops a square. So you're just plugging in the values here. You get a square here. So now you can just change the coordinates. So you redefine your coordinates to be like R equals Q minus psi rho. And also T, you also redefine the time coordinate to be T over psi. And then take psi to be 0. This is the so-called decoupling limit. So you just change your radial coordinate, R, here. You redefine it in this way. Your new radial coordinate would be rho. And also your new time coordinates, let's call it T hat, sorry. They are both redefined up to some parameter that is adimensional, and we take it to be 0. This means that you zoom in into the horizon geometry, because if you send this to 0, R is very similar, is very close to Q. And Q is really the horizon coordinate. What you get a metric of this form here. And this is the last thing that I will write. Let me discuss this first. Square. This is T hat. So the metric that you get is really this one, which is very different with respect to the ones that we find for the Schwarzschild solution. So if a solution is at 0 temperature, the new horizon geometry is, this is just the S2, right? Just a round 2 sphere. And this is the metric of AdS2 space. So the new horizon geometry of an extremal black hole is not like a disguise of flat space, two-dimensional flat space as it was there, but it has a very different configuration. It is a product of AdS2 times S2, and this is the so-called Bertotti-Robinson geometry. So we can just say it here. It's called Bertotti-Robinson. And the appearance of an AdS2 factor is really indicative of the fact that AdS space, like in general, like it means that you have an infinite throat. So in the new horizon geometry, what you get is like this factor here, in which you're really staring at an infinite throat that develops across the horizon, times a sphere of just constant radius. So this would mean that for extremal black hole, the new horizon geometry really like the physics at the horizon decouples for what really like is outside because of the presence of this infinite AdS2 throat. Which means that we can actually, like one of the things that we will do is that we will focus on the new horizon geometry. And the fact that this is really, you have this approximate decoupling of the new horizon geometry with respect to what you have just outside the horizon is one of the simplifications that will allow us to do computation. And let me mention as a last remark that this is not quite, only valid for Minkowski black holes. So this is, we have started with a Minkowski black hole, because a black hole which is asymptotically flat, but this is valid also for black holes which, for instance, are AdS. So the new horizon geometry of an extremal black hole seems to be something universal. So you have it also for AdS black holes. And also in some specific case, you will also have for de Sitter black holes, even though de Sitter black holes also allow for more, let's say, more possibilities other than AdS2 times S2. But and we will discuss, let's say, the consequences of this new horizon geometry and this, the physics of extremal black holes starting from the next class. Okay.
Okay, we thank Chiara. Are there any questions?
Which one?
I just want to know what is that metric, this one, yeah.
This one? So this one you get only by plugging in this constraint here inside here.
Oh,
And
okay.
so then if you plug in this, you recover, a square, which is exactly this one.
Oh, okay, thank you.
So it's just by plugging in the extremality bound inside the Reister Nostrom.
So that is the metric of an extremal black hole, okay.
Yes, yes. So I just plugged in the extremality bound inside there. So this is the metric of an extremal black hole.
Question? Sorry.
Q in this metric seems like is playing a role of radius of the space.
Yes. So in this case, you have that, Q is the radius of AdS2 space and also is the radius of S2. So for black holes, at least in four-dimensional Minkowski space, you always have that the radius of AdS2 is equal to the radius of S2. But if you have, for instance, anti-de Sitter black holes, means that you have also a cosmological constant, which is a further parameter. So these two radii can be, in principle, different. It's not the same. You will have a more complicated function, like the AdS2 radius will be a more complicated function of the charge and the cosmological constant.
More questions? Okay, anyway, we have an exercise session after the coffee break. So let's thank Chiara again. And let me remind you that the exercises are already on the website. So here, these are the files. So please go back, open them, try to do them, take advantage of the speakers being here at least for a while.
And so we meet again.
I have a very important announcement. Larissa told me that she would be very glad to give money to the people that she needs to give money to. Unfortunately,